linear approximation note. Yeah, this is the one. Let me continue from here. The calculations are the same as the previous. What is it? What am I doing here? I think I want to paste. Okay, let me try again. Can I do it from here? Yeah, I can do it from here also. The calculations are the same up to this point. Yeah. Okay, so from previous calculations, I will not repeat the calculations here. From previous calculation, this is the result. But now instead of now both percentage error in measuring R1 and R2 is 2%. So here we have 0.02. Okay, so I can factor out 0.02. 0.02. So you see, now R1 plus R2 cancel out, right? They cancel out. Yeah. So the answer is 0.02 here. 0.02. So the percentage error in this case is 2%. That is the answer. Okay, that is the answer here. Because the percentage error for measuring R1 and R2 0.02. So we can factor out 0.02, and then we have more cancellation. This R1 and R plus R2. So in this case, there is no need for the information R1 and R2. Okay, whatever the values of R1 and R2, they amount to the same percentage error here, 2%. That's all. Okay. Yes. So we have discussed this sample test 1. So we have already solved problem 5. Look at this problem 6 in this sample test 1. It's about finding critical points, finding the local maximum, local minimum. Okay, this is topic that I'm going to discuss today. Okay, I'm going to discuss a topic related to this problem number 6 in this sample test 1. This sample test 1 is from last year, semester 1, 2020, 2021. Last semester, yeah, this is from last semester. You are now in semester 2, isn't it? This is from the last semester. Okay, let's review. Okay, what you have learned in calculus. Suppose I have this about what you have learned from about local maximum, local minimum for a function of single variables. Okay, for a function of single variables, and then we see how this idea develops or extended to functions of two variables. So suppose we have a y equal to f of x. Okay, suppose this is a graph of a function y equal to f of x. You can see from this graph we have some maximum point here, minimum point, inflection point, and then here we have a maximum point and minimum point here, right? Yeah. So they can be found by solving this equation dy dx equal to 0. Because at this maximum or minimum point and inflection point, if we draw a tangent at the extremum point, the tangent is horizontal. Yeah, at the extremum point, the tangent line at the extremum point is a horizontal line. So a horizontal line has zero derivative. Okay, so to given a function y equal to f of x, to determine the extremum point, we solve for dy dx equal to 0. Okay, this is what you have studied. Um, so they are also called critical points. The extremum points are also called critical points. You know, the local maximum point, local minimum, inflection point, they are also known as critical points. So to find critical points, we solve dy dx equal to 0. And in addition, we also have this idea on absolute maximum, absolute minimum on a interval. So consider this graph, a different graph, y equal to f of x over the closed interval a to b. So here we have a local maximum, right? Here we have a local minimum. And here is the end point here. But this point is higher than the local maximum and local minimum. And the point here is the lowest. The point here is where f takes the lowest value. And the point here is where f takes the highest value, right? Okay. So absolute maximum in this graph is f of b. The maximum value of f over this interval is f of b. You see, this is the highest point of f over the interval a to b. So the absolute maximum is equal to f of b. It is the largest value of f on the interval a to b, the highest point. Absolute minimum is it occurs at x equal to x2. Okay, this is the point where f is smallest over the interval a to b. So we say this local minimum also as the absolute minimum fx2. Now the maximum value here occurs at the end, okay, at the end of the interval, at the end point of the interval. Yes, doesn't necessarily the maximum value is the local maximum. The absolute minimum is at the local minimum. Okay, sometimes the absolute maximum may occur at the end point of the interval. Sometimes absolute minimum also may occur at the end point of the interval here. So given a function y equal to f of x, how do we determine the critical points? Okay. Remember, fxy, the graph is a surface, right? It is a surface. So on the surface, sometimes we have maximum points, we have minimum points, and also saddle points. So for a function fxy, to determine critical points, we solve this system of equations simultaneously. F partial x equal to 0, f partial y equal to 0. Okay? And then three possibilities may occur for a critical point. Either it is a maximum point or minimum point or a saddle point. Maximum point and minimum point are also called extremum. Okay, extremum points. Yeah. So, um, having found a set of critical points, how do we determine the nature of the critical point, minimum, maximum, or saddle points? So we have a test which is called the second partial derivative test. Yeah. For a function of single variable, we have the first derivative test, but we don't have first derivative test for a function of two variables. we have second partial derivative test. Yeah. So suppose x naught y naught is a critical point of fxy. Yeah. So this x naught y naught is obtained by solving this system of simultaneous equation here. Sometimes we can have more than one solution for this system of equation. So suppose x naught y naught is the critical point of fxy, and let A be f partial x at the point x naught y naught, and let capital B be f the value of f partial x partial y at the critical point x naught y naught, and let capital C equal to f partial y at the critical point x naught y naught. Now it is a minimum, the critical point is a minimum if these conditions are satisfied. AC minus B squared greater than 0, A greater than 0. The critical point is a maximum point if these two conditions are satisfied. It is a saddle point if the condition AC minus B squared less than 0. The test, however, fails if AC minus B squared equal to 0. So we have to use a different test or by observation or something like that. Okay. So this is the method required. Okay. To solve this problem. To solve this problem number 6. No, not this one. This one here. That is the method required to solve this problem number 6. But let's discuss some other example first. Determine the critical points fxy equal to x cubed plus y cubed minus 3xy. Okay, then classify the points as local maximum, local minimum, or a saddle point. Okay. Yeah. So to find the critical points, we solve, right? To find the critical points, we solve this system. We solve the system f partial x equal to 0, f partial y equal to 0. So what is f partial x here? Anybody? You should be an expert by now.
3x squared minus
Okay.
3y.
3x squared minus
3y.
3y equal to 0. What about f partial y?
3y squared minus 3x.
3y squared minus 3x, yes. So the first equation implies I can cancel out all the common factors 3 here. So we have y from the first equation, we have y equal to x squared. Okay. So you must have studied, solving system of equations, right? So here is one application. So from the second equation, we have y squared minus x equal to 0. The first equation says y equal to x squared. So we replace y equal to, in the second equation, by x squared. Okay, so now we have one equation in one unknown. That is x to the power of 4 minus x equal to 0. Okay, so we factor out x, so we get x cubed minus 1 equal to 0. So this has two solutions, x equal to 0 or x cubed minus 1 equal to 0. Okay, recall from algebra that if AB equal to 0, that means A is 0 or B is 0. Okay, this is from algebra. And this second equation says what? X cubed equal to 1, so therefore x is equal to 1. So we have two critical points here, x equal to 0 and x equal to 1. So when x equal to 0, what is the y? We use this equation here, y equal to x squared implies y equal to 0 squared equal to 0, 1. So one critical point is 0, 0. Another solution is x equal to 1. So y is again x squared. So we have y equal to 1 squared equal to 1. So we have second critical point is 1, 1, 1, right? 1, 1. So we have two critical points. We have found two critical points here. Now we want to classify these critical points, whether the critical point is a maximum or minimum or a saddle point. So we use the second derivative test. Okay, we use the second derivative test. We can write in the form of table. We have two critical points, 0, 0 and 1, 1. So what is A? A is f partial x, right? So what is f partial x here? Remember we have found f partial x just now. F partial x is this one, right?
6x
This
is
is f partial x.
6x.
Yeah. And the one below is f partial y. So we differentiate f partial x with respect to x again. We get 6x, right? We get 6x.
Yes.
Yeah. And then b is equal to f partial x partial y. So we differentiate f partial x with respect to y. What do we get? We differentiate f partial x with respect to y, which is minus 3, isn't it? Minus 3,
Yes.
yes. And then c, we calculate c. c is f partial y partial y.
6y.
6y, okay? 6y. So at when x is 0, y is 0, 6x is equal to 0, right? And b equal to what? Minus 3 is a constant, minus 3. And c is 6y. At the critical point 0, 0, y is 0. So now we calculate AC minus B squared. A is 0. C is also 0 minus B. B is minus 3. And so we have minus 9, right? Minus 9. So what is it? What is the conclusion here?
Saddle point. Saddle
Saddle
point.
point. Yes.
Oh, it is greater.
Where is that? Here. We need this one. Yeah, we need to use this one. Yeah, we need to recall this one. All right, less than 0. It's this one, isn't it? So it is a, so 0, 0 is a saddle point. Yeah, 0, 0 is a saddle point. Yeah. So 0, 0 is a saddle point. What about the other point? 1, 1. So A is 6x. X is equal to 1. So 6. B is a constant minus 3. C is equal to 6y. So here y coordinate is 1. So here we have 6. AC minus B squared is 6 times 6 minus B squared, which is 36 minus 9. What is 36 minus 9?
27.
27. So this is greater than 0. So AC minus B squared is greater than 0. However, A is greater than 0, right? Here, A is
Yes.
greater than 0.
Minimum
Yes.
point.
So 1, 1 is a minimum point. Okay? So the conclusion is 1, 1 is a minimum point on the surface. It's a minimum point on the surface. Okay. The function fxy, the graph is a surface. So I have used a Mathematica to plot that graph as shown here. Okay. This is the graph of x cubed plus y cubed minus 3xy. It is defined for all xy. So I have restricted the domain to this rectangular region here. X from minus 3 to 3, y equal to minus 3 to 3. Okay, this is the surface. Yeah, the surface of the graph. So, and here I have plotted the critical points. We have two critical points. One is at 0, 0. The other is at 1, 1. Okay, why is it 1, 1 minus 1? Okay, I need to explain. So this implies what? Z is equal to F 0, 0 is equal to 0, right? When X is 0, Y is 0. Yeah, so actually, the point is a point X, Y, Z, right? So actually, to be more precise, I should say this 0, 0, 0 is a saddle. It's a saddle point. And 1, 1 implies what? 1, 1 implies F11 equal to what is the equation just now? X cubed plus y cubed minus 3xy. So if I replace x by 1 and y also by 1, the result is 2 minus 3 equal to minus 1. Okay, so the point 1, 1, -1 is a saddle point. It's a saddle point on the surface, right? It's a saddle point on the surface. So this is what I have plotted here. The point 0, 0, where is it? Should I, maybe I should add here as well, axis label. Label the axis. Automatic. No result. So this is 0, 0, 0 here, and this is 1, 1, -1. Okay. Now I have plotted these 2 points also on the surface. Yeah, I plotted the 2 points, the 2 critical points also on the surface. So here is the saddle point. 0, 0, 0 is over here. 0, 0, 0 is here. So here, and the other one is a saddle point here. You can also rotate this to see why. That here it is a minimum point. It's a saddle point. Here it is a minimum point. Okay. Yeah. Any question?
Doctor,
Okay, yeah.
1 minus 1 -1 is a saddle point or minimum point?
1, 1 -1 is a saddle point, right? Oh no. I'm sorry. It's a minimum point. I'm sorry. Yeah, you're right. It's
Okay, thank you, Doctor.
It's a minimum point. Thank you. Yeah. Yeah. It's a minimum point. Huh? Yeah. So here we have 2 critical points. One is a saddle point. The other is a minimum point. Okay, let's do one more example. Let me just say repeat the above question. For fxy equal to xy squared plus y squared minus x squared over 2 minus 2x plus 3. Okay, before I solve this problem, let me uh, remind you about something here. Okay. You see, there is we have this equation here, right? You know, sometimes a student tempted to do this. X4, there's a temptation to do this. X to the power 4 equal to x, and then you divide both sides by x. Okay? You divide both sides by x, and then you will get x cubed equal to 1. Then you have only one solution. That's what happened if you do this approach. Okay, here what I did, I was factorized, right? I factorized. I didn't divide both sides by x. So here you lost one solution. This is what happens. So you will get only one solution. Here you lost one solution. So this is a common mistake. Sometimes committed by students, you know. So you should do the factorization here, not divide both sides, because you will lose one solution here, which is x equal to 0. Yeah? Okay, now repeat the previous example for this function now. So we want to find the critical points. We solve this system. F partial x equal to 0, f partial y equal to 0. Right? What is f partial x for this example?
Y square minus
Y squared
x minus x.
y squared minus
X.
f partial x, huh? F partial x.
Yeah.
Y squared minus x. Anything else?
Minus 2.
Minus 2.
Minus 2. Okay, we want this. We want to set that to 0. What about f partial y?
2xy plus 2y
F partial y is 2xy. Yes.
plus 2y.
Plus 2y. Anything else? That's all, huh?
No. Yeah, this
Yeah,
one.
we set this to 0 also. Okay. You try to eliminate one of the variable. From the first equation, we see that x is equal to what? Y squared minus 2, right? Yeah. From the second equation, if I divide both sides by 2, I will get xy plus y equal to 0. Okay? So now we replace x in the second equation by y squared minus 2, isn't it? We replace x in the second equation by y squared minus 2. So we get y squared minus 2 minus 2. Y squared minus 2 times y plus y equal to 0. This simplifies to y cubed minus what? Minus y, right? Minus y, right? Minus
Yeah,
y
minus
equal to
1.
0. We can factor out. Here also be careful again. Do not divide both sides by y, but we factorize. Y squared minus 1, y equal to 0. So this means what? This means y squared minus 1 equal to 0 or y equal to 0. But y squared minus 1 equal to 0 means y squared equal to 1, which means y equal to plus or minus 1. So here we have three solutions. Y for the y coordinate of the critical points. Okay. So now we want to find the associate x coordinate for each of these y. So we have y x equal to y squared minus 2. So when y is 0, x is y squared minus 2 means 0 squared minus 2, which is minus 2. So we have a critical point minus 2, 0. When y equal to say plus or minus 1, x is equal to y squared minus 2, y is plus or minus 1, plus or minus 1 squared is 1, so 1 minus 2 is minus 1. So we have minus 1 as a critical point, and also minus 1 1 as a critical point. So here we have three critical points. So this implies, in this example, we have three critical points. The points minus 2, 0, minus 1, and minus 1, 1. All right. This is also a sample test 1 question here. The one that I'm solving right now is also a sample test 1. Sample test 1 question. So now we want, having found these 3 critical points, now we want to determine the nature of these 3 critical points, whether they are maximum, minimum, or saddle point. So one way is to create a table like what I did in the previous example. So we have 3 points, minus 2, 0, minus 1, minus 1, and minus 1, 1, okay, as the critical points. And A is f partial x partial x. What is f partial x partial x?
Negative
Let's
1.
go back to this expression here.
Negative 1.
F partial x is minus 1. Yes, that's correct. What about B, which is f partial x partial y?
2y.
2y, okay, 2y. And then C is f partial y partial y. What is f partial y partial y? 2x plus 2, right?
Yes.
2x plus 2, yeah. And for the last column, we want to calculate what? AC minus B squared. Okay. For the first critical point, minus 2, 0, okay, these are all constants for any xy. What about B? For the first critical point, y is 0. So B is 0. For the second critical point, y is minus 1. So B is minus 2. Where for the third critical point, y is equal to 1. So we have 2 times 1 equal to 2. Okay, now we evaluate the values of C for each critical point. When for the first critical point, x is minus 2. So we have 2 times minus 2 plus 2 equal to minus 4 plus 2 is minus 2. For the second critical point, x is minus 1,
Equal to 0.
0. For the third critical point, x is also minus 1. It's also 0. Yeah. Okay, now we calculate AC minus B squared for each critical point. For the first critical point, A is minus 1, C is minus 2, and B is 0, which is equal to 2. 2. For the second critical point, A is minus 1, C is 0, and B is minus 2. That this is minus 4. For the third critical point, A is minus 1, C is also 0, and B is 2. So this is also minus 4.
Minus
Okay.
4.
All right. So what do we get here? Right. Okay, let's look at this conditions again.
2 saddle point.
We have 2 saddle points, yeah, because AC minus B squared is 0 for the second and the third critical point. So that means the second and the third critical point give rise to saddle points. What about the first one? Greater than 0.
Minimum.
Maximum point.
Is it maximum?
Jump.
Yeah, maximum. Okay, maximum. Yeah. So the first critical point give rise to maximum point. Okay, yeah. So what are the okay, let's find the value of f at each critical point. Minus 2, 0 implies f minus 2, 0. What is that? You need to remember what's fxy that was given earlier. It's xy squared plus y squared minus x squared over 2 minus 2x plus 3. See, on the surface, the points are x, y, z, right? Yeah, so that's why I need to calculate the value of f at each critical point. So what is f here? Minus 2 times 0 squared plus 0 squared minus minus 2 squared over 2 here. So we have minus 4 over 2. Minus 4 over 2 minus 2 plus 4 plus 3, which is 5, right? 5. Yeah. So therefore, minus 205 is a what? Maximum point. Maximum point, right? It's a maximum point on the surface. For the second, we have, okay, I've already calculated the value. It is equal to 4.5. Okay, so the point minus 1, 1, 4.5 is a saddle point. The other critical point is at minus 1, minus 1. Okay, it is again equal to 4.5. I leave it to you to show the details. Minus 1, minus 1. 4.5 is also a saddle point here. I've also plot the surface here using mathematical. Yeah, this one here. This example here. Okay, this is the surface of xy squared plus y squared minus x squared over 2 minus 2x plus 3. This is the surface. Yeah, you can see I can also rotate here. Yeah. So where are the critical points? So below show the critical points. I plotted the critical points here. They are shown, and then we combine those two 3D graphs on this. Okay, so here are the location of the critical points here. So we have 2 saddle points and 1 maximum point. You can see from the graph here that we have 1 maximum point and 2 saddle points here. You can also see it from various angles. Yeah, I will upload this also in the e-learning. Yeah. Any questions so far?
Doktor,
Hmm.
boleh share slide yang tadi?
Slide yang tadi. Okay, this one.
Ya.
Yeah. Kenapa? What's wrong?
Oh, tak ada nak tak ada nak check je.
Okay.
Okay.
Yeah.
Betul.
Yeah. Sometimes I made mistakes also. Correct me if I did anything wrong in the calculations. All right. Let's continue. Tak payahlah, no need for 10 minutes break. Let's continue so that we can finish early.
Doctor, I have one question.
Yeah.
Do we
Yes,
need
yes,
to
yes.
sketch the graph for this or just leave it like this?
No. That graph is just for, it's, just extra. So
Okay.
of course we don't expect you to graph during the test or final exam. Of course.
Okay.
Yeah, this is enough. Yeah, this is enough. Yeah.
Okay, thank you, doctor.
Okay. Let's see. I found one interesting question in the book by Dr. Yusuf Yaakob. The problem is related to electricity. This one here. Okay. So we can use the method that we have discussed just now to solve this problem here. Let me copy this. Not enough. Not enough. Need more. Here. Okay. No. Okay, like this. Okay, let's take this as our next example related to electricity. How the idea that we have discussed can be used to solve this power station problem. This is taken from the book exercise 1.5 on page 30, okay, of that book. Okay, let's read this question first. A sub-power station is to be located at PXY, as shown in figure 1.31 here, so that the sum of squares of the distances from P to three towns A, B, C, with their coordinates given, is minimum. Find the coordinates of P. This location will minimize the amount of cable to all three towns. Yeah. The reason I have picked this problem is it's related to electricity. You are from the electric. You are in the electric course, right? Electrical engineering program. So let's see how the methods that we have discussed can be used to solve this problem. So here we have three stations, right? Three sub-power station. What is it? Three towns. Yeah, A, B, C are three towns with the coordinates as shown. So we want to locate a sub-power station P here in such a way the total distances of P, the sum of the total distances of P from the towns as minimum as possible. Okay. What is the distance PA? The distance PA, use the distance formula, is square root of x squared plus y squared. So the square is x squared plus y squared. The distance between P and B is the square root of x minus 2 squared plus y minus 6 squared. So the square of the distance PB is x minus 2 squared plus y minus 6 squared. And the distance between P and C is the square root of x minus 10 squared plus y minus 0 squared. And the square of the distance BC is x minus 10 squared plus y squared. Okay. Now we want the sum. You want to minimize the sum of squares of the distances from P to 3 towns. So let's denote the function fxy as the sum of squares. So that means PA squared plus PB squared plus PC squared. These are the sum of the squares of the distances from P to 3 towns, right? So PA squared is x squared plus y squared. PB squared is x minus 2 squared plus y minus 6 squared. And PC squared is x minus 10 squared plus y squared. Yeah. Why we want to deal with squares? Because then we don't have square roots. We don't need to deal with square root. Yeah. If I let gxy, okay, if I let gxy as PA plus PB plus PC, then gxy will involve square root, isn't it? Will square root. So the function, the point xy that minimize f will also minimize g. That's the idea. Okay, that is the observation. The point xy that minimize f would also minimize g. Would also minimize the function g. Yeah. So it's easier to work with f because that doesn't involve square root sign. So fxy is a function of two variables here, right? Yeah. So we want to find the point xy that that serve as a minimum point of fxy. So let's first simplify xy. Okay, let's expand x minus 2 squared, which is x squared minus 4x
plus 2.
plus 4. Plus 4.
Oh, plus 4.
Okay, right? If you expand y minus 6 squared is y squared minus 12y plus 36. Huh? And if you expand x minus 10 squared is x squared minus
20x
20x plus
100.
100 plus y squared. Now we want to combine all the like terms. For example, we have x squared here, x squared there, another x
3x
squared there.
squared.
So 3x squared, right? So we have 3x squared. Y squared,
3y squared.
we have y squared here, y squared there. So we have 3y squared. We have 3y squared. Okay, what else?
Minus 24x.
Minus
24x.
we have minus 4x here. Yeah, so we have minus 24x, huh? Minus 24x. What about the y term?
Minus 12y.
Minus 12y only, huh?
Yeah.
Or minus 12y only. This minus 24x minus 12y. Okay, what about the constants?
Constant 140.
140, eh?
Yeah.
140, okay. Okay, now we try to find the critical points. Okay, find the critical points and then we solve this set of equation. What is f partial x? This is our
6x.
fxy now.
6x minus
6x.
24.
6x minus 24. What about the second equation? F partial y equal to 0.
6y
6y
minus 12.
minus 12. Huh? Yeah, so this is an easy set of equation to solve. X is equal to 4. The other one is y equal to 2. Yeah, so this is a simple simultaneous equation to solve. So we only have one critical point. Yeah, in this problem, we have only one critical point, namely 4 and 2. Yeah. Now the question is whether this gives rise to the minimum. Because we want to minimize, right? So we are interested in the minimum point. So let's construct this table. A is f partial x partial x. What is partial x partial x? 6, right?
6.
Yeah, partial x is 6x because this is f partial x and this one here is f partial y. So f partial x is a constant 6. What about b, which is f partial x partial y?
0.
0. And c is f partial y partial y?
6.
6, yeah. So it's all constant here, right? So for the critical point, A is 6, B is 0, C is 6. Then we have A. Then we want to calculate AC minus B squared. 6 times 6 minus 0 squared, which is 36. Yeah. What is it? Do we have a minimum here?
Yes.
Do we have a minimum here?
Yes.
Let's go back to this one. Copy. Yeah. Paste it here. Okay. So AC minus B squared is greater than 0. And then A here is also greater than 0. Yeah, so F is minimum. Okay. So F is minimum at the critical point for 2. Yeah. So the it is recommended to place the power sub power station P at the coordinate 4 2. Okay, 4 2. That would minimize the amount of cable to all 3 towns here. Right? Any question for this example? No.
Doctor, is this possible when we calculate until the end it is a maximum point?
Maximum?
Yeah. Since the question is asking the minimum.
Minimum,
is it possible?
Maximum, of course, if you can doesn't make sense, right? You really
yeah.
want to minimize cost, isn't it?
Yeah.
You can place P maybe far, far away from ABC. Then you have, then you need more amount of
Cost.
cable, right?
Yeah.
If P is, you can place P at maybe points far away from ABC, but that will require a longer cables, right? Yeah, usually we're interested in the minimum. Yeah.
Doctor, so that
Yeah.
if we plot this 3D graph, is it a
Uh-huh.
paraboloid? Yeah, maybe. Yeah,
Is
maybe.
it a paraboloid?
Maybe, yeah, I think.
Maybe. Well, we can give a try. Let's see. Yeah. Let's
it
see.
takes time, so sorry.
Oh, simple. It's Mathematica can do this very quickly. Let me do it over here.
3x squared.
Now,
Okay.
what is the equation?
3x squared plus
3x squared
plus 3y
plus
squared
3y squared
minus
minus
24x
minus 24x
minus
minus
12y
12y
plus
and then
140.
plus 140. Okay, so it is defined for all xy, right? So let's limit the rectangular to this rectangular region. This rectangular region contains the minimum point, right? For for 2.
4.
So let's extend this to 5 so as to include the minimum point. Shift enter. See? It's already done. Yeah, so
Maybe it's paraboloid.
yeah, I didn't plot the whole. Maybe maybe it's a parabola. Yeah, we can complete the square, right? We can complete the square to get the standard form of a paraboloid. Yeah, you can experiment this on your own. Huh? You can
Okay.
experiment this on your own. Suppose I want to plot exactly the point here just now. P2 equal to
4, 2.
4, 2. 4, 2.
And then
I need this command. I need to use this command. What about the z coordinate?
calculating. Calculating.
Can you tell me what is the z coordinate?
Still calculating.
Okay.
80.
80.
80.
Yeah,
Yeah.
80.
Okay. So now let me combine those two graphs. Show P1, P2 like this. There you see. See, this is the point, right? For 2. Yeah. You see, it is a minimum point. It is a minimum point there. 4, 2. If I extend this to 10, what happened? If I extend this to 10. Yeah, you paraboloid, right? We can see more, isn't it?
Yeah. Paraboloid.
Yeah, it is a paraboloid. Okay? It is a paraboloid. No wonder it gives only one minimum point. Yeah. There's no other minimum point, just one minimum point here. Okay, any more questions? enough for tonight, right? Let's have a rest. Enough? Is it enough?
Yes, doctor.
Okay. So we have another class, right? This coming Wednesday. So
Yes,
this
yes.
coming Wednesday, I will talk about multiple integrals.
Okay.
We'll move on to the new chapter about the multiple integral. Okay. Yeah. We are actually behind a little bit behind. Okay, according to the weekly plan, we should have started about multiple integral. I don't know when, last week or this week. Let's look at the table at the at our lecture plan. I have already have a printout. Yeah, I have a printout. According to our lecture plan, we should have started double integral. Yeah, this week. Yeah, we should. Uh, this week should cover the double integrals. We should start talking about double integrals this week. Okay, so we are not too far behind actually. So this coming Wednesday, I will start talking about double integrals.
Doctor, do we have attendance tonight?
Oh yes. So please be patient. I want to next show you the QR code for the attendance.
Okay.
Where is it? Why is it not showing? Kehadiran kelas. Tak tunjuk. Tak tunjuk. Oh, ada. I just need to be patient. Just wait for a while. Maybe internet a little bit slow. Okay. SSCE 1993. So our class today starts at 8 p.m. All right, there you are. Please scan your QR code for the attendance. And you may leave the class after you have scanned. Thank you once again for joining our